We're going to finish up chapter 22 today. So we're going to talk about, again, the nonmetals, the difference between the biological importance of dehydration when we talk about phosphates. We've seen in our nucleic acids, RNA and DNA, there's actually a dehydration. Again, when you take water, there's a difference in RNA and DNA. DNA is deoxyribose. It has less oxygen. That's where it comes from. We have ADP and ATP. This is a transition where we get our energy from our cells. Again, you can see it here. If you've had biology, you've talked more about this, but this is what happens in the mitochondria, where you get that OH on there, or that dehydration process, okay? Okay, the last element we're going to talk about, the one that we have lots and lots of, is carbon. Okay, you can take classes just on carbon, which is organic chemistry. There's lots of allotropes, lots of forms of carbon. We have graphite, which is, if you're writing with a pencil, that's what you're writing with. Diamonds, graphite and diamonds is just a lot more pressure and a lot more temperature. Fullerenes, carbon nanotubes, there's graphene. We have carbohydrates, CO3s, coal, petroleum, natural gas. Those are all forms of carbon. Lots and lots and lots of forms of carbon. Okay, some of the uses, we use it in black ink, carbon black. We use it in filters to get rid of odors. If you have a drinking water filter like a Brita or a Pure, they have carbon, activated charcoal in there. We have strong composite materials, carbon fibers we can use in cutting tools. Diamond's one of the hardest substances known to man, can use in cutting. There's all kinds of, carbon is just, it's everywhere in so many different forms. Okay, if you look at the difference between a diamond and graphite, okay, they're both pure carbon. A graphite has a little bit of luster. It will conduct electricity. And its sheets are held together by dispersion forces. If you remember, dispersion forces aren't very strong. Okay, those are the ones between molecules, like of nonpolar substances. Okay, and its density is 2.25 grams per centimeter squared, or milliliter, whichever we want to say it. It's very soft, it's black, and it's a slippery solid. It's like what we call lead in our pencil, but it's not really lead, it's graphite. Okay, a diamond is very crystalline, so it's not metallic. It's an insulator. So graphite conducts electricity, a diamond. Its hybridization is different. It's held together in a stronger, obviously in a much stronger network, because if you think of a diamond versus your lead in your pencil, 3.51 grams, so it's much more dense. It's very clear, hard, solid, and worth a lot more money, obviously. You can buy all kinds of graphite for your pencils. You know, a diamond's going to cost you a little bit more. Okay. We have lots of oxides of carbon. Carbon monoxide, CO. It's an odorless, colorless, tasteless gas. Unfortunately, it's not very good for you. What it does is it acts like a Lewis base with transition metals. But if it gets into your body, it binds with iron in the hemoglobin. So instead of iron carrying oxygen like it's supposed to, it carries carbon dioxide. So basically, you don't get any oxygen, you're going to die because of it inhibiting the iron in your hemoglobin from carrying oxygen. Instead, it's easier to bind with it, so it carries carbon dioxide. So you look really good when you die because you got rosy cheeks, but unfortunately, you're still dead. Okay, it's also used as a fuel, and they use it as a reducing agent when they're trying to get pure metals. Carbon dioxide, just add another oxygen to it. It's colorless, odorless gas. Excuse me, we have a lot of it in the atmosphere. Unfortunately, we have more now than we have in the past, and that's led to the greenhouse gases, the greenhouse effect, where the earth is getting warmer. We use it in carbonated beverages. That's the bubbles in your pop. It can be used as a refrigerant like dry ice. They use it in baking soda. They use it all kinds of sodas. Okay, so it's the big thing again is carbon dioxide uses a carbonated beverage. We make carbon dioxide as one of the things we breathe out. Okay, we have carbonic acids and carbonates. They come usually from minerals. Okay, the dissolved CO2 in water is in equilibrium, hopefully, with carbonic acid. Carbonic acid is what's in the air, H2CO3. It comes from CO2 and water. It makes carbonic acid. That's why naturally occurring rainwater is a little bit acidic because of this. It's a weak acid. But if you take a strong acid, like, if you add sulfates, that's when you get sulfuric acid, and that's when you get acid rain. Okay. Carbonates are found in minerals like calcite. You'll find them in limestone, marble, in shells of marine animals. Okay. One of the ways, if you've taken geology, if you can test if it's got carbonates, you put a little bit of hydrochloric acid on it, like it's shown here, and then it bubbles. So then you know it has carbonates in it. Okay. Washing soda and baking soda, those are forms of sodium, like baking soda is sodium bicarbonate. There's sodium carbonate, which is washing soda, which isn't nearly as common, but I know you guys all know what baking soda is. And the reason why it bubbles when you add it to vinegar, it's got that carbonate in there. Okay. Lime, which is calcium oxide, is formed from calcium carbonate. Calcium carbonate is chalk, you guys. It's also used to make mortar, like when you put up bricks and stuff like that. So it's a part of that. Okay, we have carbides. Those are binary compounds of a carbon and a metal, or a metalloid. Some nonmetals, not a lot, but some nonmetals. Okay. Calcium carbide is a source for acetylene, so they use it in welding. Many of the transition metals will form what they call interstitial carbides. They're very hard, very heat resistant, like tungsten. I'm sure you've heard of tungsten carbide. It's something that they use in a lot of industry. There's covalent compounds like silicon with carbon, boron with carbon. They are almost as hard as diamonds, and they're used in cutting tools. Okay, so again, they're very strong materials. The other things in group 4A, another one that doesn't get nearly the credit as carbon is silicon. Silicon and germanium are metalloids, but they're also the semiconductors. Silicon and germanium are the reasons why we have all our cool toys, our cell phones, our computers, our video games, all that fun stuff. Semiconductors, okay? That's silicon and germanium. We also have tin, which I'm sure both of you know about. Lead, those are all in that group. So you got quite a group there. You've got carbon on the top as a nonmetal, then you got two metalloids, silicon and germanium, and then you got tin and lead on the bottom as two metals. Okay. Common oxidation for the guys, germanium and below is +2. Carbon is +4. Okay. The reason why carbon forms so many different compounds is it needs to form 4 bonds. Okay. Silicon is +4 sometimes, but it can't form as many because silicon's bigger, so they're not as stable. But because carbon is small and it needs to form 4 bonds, it forms a lot of stuff, lots and lots. Okay. Carbon is the only group member that commonly forms bonds with itself. Okay, so you'll get carbon-carbon-carbon bonds, and that's a whole thing of organic. Silicon doesn't do that so much. Okay, silicon is the second most abundant element in the Earth's crust next to oxygen. Okay, silicon usually is silicon oxide, silicate materials or minerals. Silicon oxide could be sand. Okay, a lot of times to get silicon, you heat it and then you add carbon to it. And then you get your semiconductors, which are made, like I said, semiconductors, your silicon chips, your transistors, everything that they put into all our modern electronics, and solar cells. The top layer of solar cells is silicon. Okay, so it's purified. They have a process called zone refining to purify the silicon. So basically, they're going to take sand, add carbon to it, and they're going to get this pure silicon, and then it has tons and tons of uses. Okay, we have silicates. Those are where you have a central silicon and it's surrounded by oxygen. They share oxygen and they form sheets. So silicates, you've probably seen this in rocks again if you've had geology. They like peel off. They're kind of cool how they can peel off. Talc, asbestos would be examples. They're softer and they can peel off right in sheets because of the way that the silicon and the oxygen forms their little, well, you can see they form in little sheets and you can peel them right off. Okay, glass is basically, molten silicon. Sodium lime glass, there's different kinds of glass, but you can take sand and you can get sodium lime glass in windows in our bottles. We have from sand again, lime, calcium oxide, sodium ash, all of those can make different kinds of glass. Cobalt glass adds cobalt to it, it gets kind of a tinge to it. If you want your glass to be harder, they'll replace potassium oxide in there instead of calcium oxide. There's lead crystal. I'm sure you've there's goblets that are made out of lead crystal. They're very, very expensive. They have like a ting to them when you hit them. But the problem with lead crystal, you got to be careful, because if you use certain things that are acidic, they'll break it out and then you'll be drinking lead. Not a good idea, you guys. Okay, there's borosilicates, pyrics, a lot of our laboratory glassware. You want to make sure it's pyric so that when you heat it, it doesn't break. Not a good idea to have things, flying all over the lab. They can withstand much higher temperatures, and again, it's the way they're made. Okay, we have silicons, the chains of oxygen, silicon, oxygen. They put them in chains, and they're really good lubricants, really good sealants, because again, they slide across each other so easily. Okay, we have boron, which is right below silicon. Next to, sorry. Boron is group 3. It's the only non-metal in that group. Then you have aluminum. The rest are metals. Okay. Boron and hydrogen are called borons. It's the simplest. Diboron, which is B2H6. It's a kind of a bridging hydrogen atom. It's got a weird bonding because it doesn't form an octet, which is weird. But they move around enough so that they're okay. If you put boron with hydrogen and oxygen, you get borane anions. Okay, they're good reducing agents. They'll get you that hydride ion if you want to make metal hydrides. The thing with diboron is extremely reactive, so it's very, when it burns, it gives off a lot of energy, and then it'll produce boric acid. Boric acid is an anhydride. In other words, it's an acid that's lost some of its hydrogen. It can be amphoteric. In other words, it can be an acid or a base. Borax salts. There's boron, team borax. You use it in your cleaning products. You've probably seen the box of it. I use it to make crystals, like crystal gardens. Oh, I guess we're done. Cool. So now we're done with chapter 20. I thought there was a little bit more there, but I guess not. Anyway, we are done with chapter 22. We only got one more to go, you guys, and that's a short chapter. So you're almost done listening to me.